In this video, we're looking at the decomposition of hydrogen peroxide in order to illustrate how to find average and instantaneous rates of reaction. We'll do it using data expressed in a table like this, and then we'll also look at a graph and graphically determine these rates as well. So somebody is looking at the decomposition of hydrogen peroxide. Let's write a balanced equation for that. Hydrogen peroxide is H2O2. And as it decomposes, it'll form water and oxygen gas. And when you balance this equation, 2 molecules of hydrogen peroxide decompose to give 2 water molecules and 1 molecule of oxygen gas. Now, in this table, we can see some data has been collected. Somebody has measured the concentrations of the hydrogen peroxide and the oxygen over time. And they're measuring the time in seconds, from 0 seconds to 2800 seconds. It looks like they started with a container full of hydrogen peroxide at 2.32 molarity and oxygen with 0 molarity, so there was no oxygen there initially. As the peroxide decomposed, its concentration drops, and as it decomposes, you're forming oxygen, so its concentration is increasing over time. Now, let's calculate from this data an average rate of reaction. Let's calculate the average rate of change for the hydrogen peroxide over the first 1200 seconds, we'll say. The first 1200 seconds. Okay? If you think you know how to do that using the numbers in this table, pause the video and try that yourself. Alright, the formula for average rate would be average rate is equal to the change in concentration of hydrogen peroxide, in this case, over the change in time. When you're finding a change in concentration, you always do the final concentration minus the initial concentration. So looking at our data table, it said over the first 1200 seconds. So that means starting at 0 seconds and going up to 1200 seconds. And so we can see that the hydrogen peroxide concentration fell from 2.32 to 0.98 over that interval. So the change in its concentration would be the final concentration, 0.98 molarity. Take away the initial concentration, 2.32 molarity, over the change in time, which in a similar way is the final time, so 1200 seconds, minus the initial time, which is 0 seconds. So with a calculator, 12.98 take away 2.32 gives me negative 1.34 molarity on top over 1200 seconds on the bottom, and then dividing, we get negative 0.001, let's see, I'll keep 3 significant digits, I guess, 0.00112, and then the units, looking on top we have a molarity, on the bottom we have a seconds, so that'll be molarity per second. There's the average rate. Notice that it's a negative rate because the hydrogen peroxide was decomposing, it was disappearing, and we were just asked to find average rate. Average rate by itself is a neutral statement. It doesn't imply whether you're producing or using up something. So the average rate can be positive or negative. It's positive if you're producing a product. It's negative if you're using up a reactant. Now, if I had asked the question in a slightly different way, I could say instead of saying just the average rate of change, I could have said the average rate of decomposition. Okay, now, as soon as I say rate of decomposition, then I'm implying in the word decomposition that the hydrogen peroxide is decomposing. So now I'm going to change the negative sign to be a positive quantity. So now the average rate of decomposition would be positive 0.00112 molarity per second. So if you just say average rate or average rate of change, that by itself is a neutral statement. It does not imply whether something is increasing or decreasing. So for there, you would have to keep your negative sign to indicate that the hydrogen peroxide was decomposing over time. If you're saying, though, average rate of decomposition, then there the decreasing concentration is implied in this word decomposition. So now you would say positive 0.00112 molarity per second. And that, of course, was the average rate of decomposition of the hydrogen peroxide. And that was over the 1200 seconds. Now, suppose, having calculated this, we're asked the following follow-up question. Let's calculate the average rate of formation, or production if you prefer, of O2 in the same interval. So over the same interval, the first 1200 seconds, calculate the average rate of formation of oxygen. Now you could set this up in exactly the same way that we did the previous question. We could say the average rate is the change in concentration of oxygen over change in time, and the oxygen's change would have been 0.67 molarity minus 0, right? That's the final minus the initial concentrations. So 0.67 molarity, take away its initial 0 molarity, and then on the bottom 1200 seconds minus 0 seconds, and that would give me 0.67 divided by 1200. That gives me an average rate of 5.58 times 10 to the minus 4, and that's again molarity per second. Notice that it's a positive quantity because the oxygen was being produced. Also because I said in the statement the average rate of formation. So the word formation implies that the concentration is increasing. Therefore, I don't need to include a positive or negative sign in the rate. It'll just be positive like this. Now, there was another way, though, that we could have found that rate, and that's because we already knew the rate of decomposition of the peroxide. We had calculated already that the peroxide was decomposing at a rate of 0.00112 molarity per second. If we look at the balanced equation, we notice that the ratio of coefficients, every time 2 molecules of hydrogen peroxide decomposed, 1 molecule of oxygen appeared. Therefore, just from the balanced equation, we could see that the rate of formation of oxygen is going to be 1/2 the rate of decomposition of peroxide, because of that ratio, 1 oxygen for every 2 peroxides. So if we come back down here and try that, we could have said another way to find that average rate for the oxygen would have been to simply take 1/2 of the rate of change, or the rate of decomposition of peroxide, 0.00112 molarity per second. And let's see what that gives us on our calculator. 0.00112 divided by 2, and this one says 5.6 times 10 to the minus 4 molarity per second. And you'll notice those two answers are equivalent, okay, when rounded off to 1 decimal place. So if you already know one of the rates of change in the reaction, you can calculate the rates of change of the other substances in the equation simply by looking at the reaction stoichiometry, the ratios in the balanced equation. For example, if we wanted to know the rate of formation of the water, we could say, because there's a 2-to-2 ratio between water and the peroxide, that the water's rate of formation is the same as the rate of decomposition of peroxide. So water would be forming at a rate of 0.00112 molarity per second in that same time interval. Similarly, if we compared water to oxygen, we could say that water would appear twice as fast as the oxygen was appearing because of the ratio 2 to 1. And so if we took oxygen's rate of formation and doubled it, we would get the same answer, 0.00112 molarity per second for the water. So there we've calculated average rates using data like this in a table. Now if that data were graphed, what would it look like? Well, I've got that done for us here. So here is the graphical representation for the decomposition of hydrogen peroxide. Okay, we've got the concentrations graphed on the y-axis versus time in seconds on the x-axis. If we asked the same question on this graph, what was the average rate of change of the hydrogen peroxide over time? And suppose we didn't have the data table available to us. And let's look at the same interval from 0 to 1200 seconds. How would we do that? Well, looking right here on the graph, we recognize that the falling curve that starts up here and falls, is the hydrogen peroxide. Because it's falling, it was a reactant, it was decreasing in concentration. The rising curve has to be a product because it's being produced, it's increasing in concentration, and we're told here that that's the oxygen gas. So let's look at the falling curve, and for the first 1200 seconds, at 1200 seconds, here is the concentration of the peroxide. And originally at 0 seconds, this was the concentration of peroxide. Now, if I join those 2 points with a straight line, let's grab a ruler here and draw a straight line through them, we can give a graphical interpretation to what an average rate is. The average rate of the reaction, according to the graph, is simply the slope of this line. So the slope equals the average rate of reaction. Okay, the slope of the line that connects 2 points on the curve is the average rate in that time interval between the 2 points. You can see that because if you simply use your equation for finding slope of a line, and let's look at the coordinates of these 2 points. This point at the end has coordinates of 1200 seconds, comma, and if we estimate the y value here, it looks to be between 0.8 and 1, in fact between 0.9 and 1, and closer to 1. So I'm going to estimate that that's about 0.98 molarity. Okay, just estimating from the graph there. And up here, looking at the the x value at the original point was 0, and the y value is just a little bit above 2.3. So 2.31 or 2.32 molarity is up there. And now finding slope of a line, slope is equal to our average rate. And we can tell that this line is falling, so its slope is going to be a negative number, right? Which matches what we saw earlier when we found the average rate of change for the hydrogen peroxide. So the average rate is the slope, and the slope formula is y2 minus y1 over x2 minus x1. The change in y values over the change in x values. Some people prefer to think of that as rise divided by run. Okay, so you might want to use that idea as well. So looking up at the top there, my y2 minus y1, I'll take the second point and call it point number 2, and the first point, point number 1. That's arbitrary. You could reverse those if you prefer. And then 0.98 then is the y value for point 2 minus 2.32, which is the y value for point 1, divided by 1200, the x value for point 2, minus 0, the x value for point 1. And if you do that on your calculator, you'll see that the answer is the same as the one we had earlier. It's negative 0.00112. Now the units for this slope In a math class, you don't usually look at the units, except perhaps in an applied math class. But here, this slope's rise, the y values, were concentrations. So their units were molarities. So those are molarities. And the x values were time, and their units were seconds. Therefore, this slope has units of molarity per second, which makes sense because we're claiming it's the average rate of the reaction. So to find an average rate of reaction from a graph, simply connect 2 points on the graph and find the slope of the line in between them. Of course, you didn't really need to draw the line. You could have simply used the coordinates of the 2 points and then jumped into your slope formula. I just wanted you to see physically what we mean when we say the slope of the line. So for example, suppose you wanted to find the average rate between 800 seconds and 2200 seconds, the average rate of change of the oxygen. Well, you would go up to here and start with this point on the oxygen curve, and at 2200 you go up to here and take that point on the oxygen curve. You'd read their coordinates. This is 800, and it looks to be just slightly over 0.5, so maybe 0.51 molarity. And you can see there's going to be some error involved here because we're estimating coordinates. Over at this other point, its x-coordinate is 2200 seconds, and its y value is just a little bit over 0.9, so maybe about 0.92 or 0.93. And now using this x1 and this y1, and this x2 and this y2, we could do exactly the same thing using our slope formula to find the rate of change of oxygen. Notice that for the oxygen curve, because it's a rising curve, there was a product, the slope of that line connecting the 2 points is going to be a positive value, right? Slope of a rising line is always positive. Slope of a falling line is negative. So those are average rates of reaction. What if we wanted to find an instantaneous rate? An instantaneous rate. What's the difference between an instantaneous rate and an average rate? An average rate has to be over a time interval. For example, over 0 to 1200 seconds is how we found the average rate in the previous example. An instantaneous rate is not over an interval of time. Instead, it's at an instant in time. There's only one point where we're talking about an instantaneous rate. For example, if we look back up here at the graph, and I hope it's not getting too cluttered, what if we wanted to know what the instantaneous rate of reaction was at 400 seconds? So for example, what was the rate of change of the hydrogen peroxide at exactly 400 seconds? So we go to 400 seconds and we go up to the hydrogen peroxide curve, and we notice we're talking about this point right here. We want to know how fast was the reaction going at that one point. I hope you realize because we know only one point, we can't use the exact same procedure that we did earlier, where we found slope like this, because we don't have 2 points. We've just got the one, so we couldn't use that slope formula right now. How do we do this if we want to find an instantaneous rate? The key is to take your ruler and go to the graph at that one point and draw what in math class is referred to as a tangent line. There's only one possible way to draw a tangent line theoretically, because it has to touch that curve at only one point. Okay, it can't touch at any more than this one point where we're looking at 400 seconds. Now, if you're doing this by hand, there's going to be some error involved, but I think that looks pretty close to be a tangent line at the point 400 seconds. So I'm going to go in and draw this tangent line like that. There's my tangent line at 400 seconds. Now I'm going to ignore the curve, and I'm only going to look at my tangent line. the slope of the tangent line at 400 seconds is the instantaneous rate of the reaction. That's the important point you want to make a note of. The instantaneous rate is the slope of the tangent line at, in this case, 400 seconds, but generally at the instant being considered. Okay, so if you're asked to find the instantaneous rate at 2,000 seconds, then at 2,000 seconds, go to your curve and draw a tangent line at that point. Find the slope of the tangent line, and you have the instantaneous rate. So let's go back to this tangent line. Now, how do you find the slope of that tangent line? Well, what I'm going to do is just take 2 points arbitrarily. I'll pick any 2 points. I like to pick points where I can read the x values accurately. For example, here's a point at 100 seconds. If I just go straight up and put a point like that on the tangent line, that point right there, what are its coordinates? Well, 100 seconds, comma, and then it looks to be just under 2.1. So how about 2.08? 2.08 molarity. Those are the coordinates for that point. And another point on my tangent line, how about over here at 1,000 seconds? If I go up from 1,000, there's a point on the tangent line, and for that point, its coordinates would be 1,000, comma, and just slightly over 1. So how about 1.01 molarity? Now that I've got the 2 points labeled on my tangent line, I can go back down and find the slope. Slope is y2 minus y1 over x2 minus x1, and using those 2 points that I just picked, either one can be 0.1 or 0.2, so I'll just arbitrarily use the 1,000 second as my 0.2. So its y value 1.01 minus the other y value 2.08, and those are molarities, over 1,000 seconds, the x value of the second point, minus 100 seconds, the x value of the first point. And then with a calculator, 1.01, take away 2.08, gives me negative 1.07 molarity over 900 seconds. And then when you divide that, divided by 900, you get negative 0.00119 molarity per second. Okay, so there's the rate of the reaction, the rate of change of the hydrogen peroxide. So this is the instantaneous rate of change of the hydrogen peroxide at that tangent point time, which was 400 seconds. Notice it's negative again because we're just saying rate of change, which doesn't imply positive or negative. If we said instantaneous rate of decomposition, then this would become positive 0.00119, because the word decomposition implies that it's a falling concentration. Notice we could also find the instantaneous rate for the oxygen at that time without going through the whole process again of a tangent line, although we could. We can use the balanced equation. We remember that for every 2 hydrogen peroxides that decomposed, there was 2 waters and 1 oxygen. Therefore, the instantaneous rate of change of the oxygen, the instant rate of change of O2 at 400 seconds would be, because of the ratio 1 oxygen for every 2 hydrogen peroxides, it would be 1/2 of the rate that we just calculated. And I won't evaluate it, but you get the idea. So finding an instantaneous rate means finding the rate at one moment, one instant. You go to that time on your graph, You draw a point on the curve you're considering. We were considering the hydrogen peroxide's decomposition, so we used the falling curve. And you draw a tangent line at that point, carefully with a ruler, a line that touches the curve only once at that point. You find the slope of the tangent line, and you've got the instantaneous rate. The other type of rate was an average rate, and an average rate is found over an interval of time. A T1 and a T2 has to be given when you're finding an average rate. All right, so I hope that helps in calculating instantaneous and average rates using both data tables and graphical interpretations.